So here we have our reflux setup. So we have our Bunsen burner, which would be connected to gas, and we have our round bottom flask with our reaction mixture just above our ceramic pad, and we have our condenser, and we have water going in the condenser at the bottom from the pump up and out through the top. Then at the top of the condenser, it's actually open, and we look at our clamps here. We have one clamp here which is fit really snug and tight, but this top one, about 2/3 of the condenser, is loosely clamped so that gravity can just pull it forward and we don't have escape of the reaction. Then we move forward to our quenching process, which is neutralization of charges. And we just need a beaker to contain the ice to put our reaction in. And if we want to take our crude product and get the pure product, we can go through purification using recrystallization, where we will just use a hot plate and some beakers, and then also set up our suction filtration apparatus with our Buchner funnel, our sidearm flask, and filter paper, and vacuum.
So to get our starting materials to create this product, we're going to want to start with our phenol group, and we're going to want to put it into a round bottom flask, and then we're going to add some ethanol for a solvent and a base. So for example, we can use sodium hydroxide, and then we're going to reflux for 15 minutes. The sodium hydroxide is going to deprotonate your phenol to get the O negative, so you're going to have a base with the hydrogen attached to it, and then we're going to add our alkyl halide to the same round bottom flask and reflux for 40 minutes this time. So after that, we're going to quench. So in a beaker, we're going to put in so many grams of ice and our product to neutralize the product. And afterwards, we can recrystallize to get a good product.
After quenching, you can take your crude product and purify it to get your pure product through recrystallization by suction filtrating and using ethanol as the solvent.
So this is our mechanism to start off our phenol. This is base will deprotonate it by taking the hydrogen off the oxygen. And in the next step, we can see it's taken off and we're left with a negative charge on this oxygen. So in the second step, we're going to have a strong leaving group right here. Typically a strong leaving group is a halogen like bromine or chloride. This oxygen that is now negative, the electrons are going to push to the carbon and the leaving group will leave, shown right here. And we're going to be left with our end product.
So we want to avoid having excess sodium hydroxide in the reaction mixture for important reason. So for a mechanism, we had our phenol and we would react it with the hydroxide or the base, and it would produce this molecule. But if we had excess, we would have excess these amounts. And once we added our alkyl halide, this OH would actually react with our alkyl halide, so it could be a bromine or another strong leaving group, and actually do a substitution, creating this product, which we don't want, so that's why. Just cut. So we would like to have excess sodium hydroxide during the workup of the Williamson synthesis when we're quenching with ice, because this high pH or basicity would ensure dissolution of any unreacted phenol. And for the last part, to determine if we need a longer or shorter reflux period, we would just have to guess and test and see how much product we produce to determine if we have to shorten or lengthen our reflux time.